Welcome to the second video of our Math 10 journey. Just a little reminder before we start that things may seem harder, but nothing is impossible. So, we got this. So today we will be reviewing one of the harder subjects taught in Math 10B. This covers balls and urns. Since the topic is pretty dense, I'll only be going over numbers 1 through 3 in the chart I will display shortly. Pro tip, please, if you learn this, put this on your cheat sheet. Pretty please. If you have Zvezda as your professor, it will for sure be in at least one of the exams. And it doesn't hurt to have it just in case. So it is super important. I know you guys aren't having Zvezda, or maybe if she comes back you will. But this is like a super important topic, and I highly advise that you master all of these techniques. So yeah, so let's begin. Okay. Over here we have a chart of the balls and urns given to me last semester, where balls, shown by B, and urns, by U, represent the distributions of balls to urns in different situations. The first column indicates whether urns are distinguishable, shown by D, or indistinguishable. And the circled numbers in the cells correspond to the section numbers that we will walk through one by one, starting with number 1, distinguishable balls and distinguishable urns. And for now, don't worry about injective and subjective, surjective. I will explain it in a bit. So let's look at the first example problem. Oh yes, put on cheat sheets. So in 1.2, number 1 states, going a little ahead there, so the first problem states that there are X kids that all need to be adopted by Y potential couples. How many ways are there for the kids to go home with the couples? Sorry if you can't read my writing. I can barely read it too. But this is assuming that the couples don't change. So in this case, like, the couples don't, like, get divorced and, like, get married to other people. So, just so it's easier mathematically to do, you know, the counting. So, yeah. I know that we haven't talked about counting or combinations or permutations in detail yet, but I have full faith that you will, with the previous video that I uploaded, be able to understand it. So, the first step that usually helped me solve these types of problems was to categorize the problem, and in this case, assign the variables. I know it's hard to determine which ones are balls and urns, especially because not all variables are balls and urns, but an easier way of categorizing would be to figure out which variable is assigned to which. In this case, the kids are being assigned to the parents, so the parents in this question would be the urns and the kids would be the balls. Yes, cool. We did it right. Okay, good job. So, yeah, as I said, the variables assigned would be the balls, and the accepting would be the urns, if that makes sense. So, now we move to the next step. The next step is to categorize the question. Or, the next step, actually, to categorizing the question would be to figure out which variables are indistinguishable and distinguishable. By seeing the words, how many ways... Ooh. Oh, yeah, okay, cool. In this question, by seeing the words how many ways, you know that they want all the possible scenarios that happen. Meaning, here, I'll just show this to here. Yes. Meaning that one kid going with one parent would be different than one other kid going with another parent. So this being said, both of them would be distinguishable, because you want all the possible scenarios, and one scenario is different than the other. And if you have your chart on you, bam, see, like I said, the cheat sheet is super important. You are done. You have your answer. You don't always need to simplify, so, like, as long as you have the chart, most of the time you'll be good. You'll have your answer. So, yeah, you did it. If not, if you don't have your answer, if you don't have it on your chart, if you're not allowed a cheat sheet, no worries. Here's one way to mathematically solve the problem. So, here we go. Cool. So, yeah, the strategy to computing the answer to this problem is to actually start with your kids, or in this case, the balls. Proceed each kid by following this formula written below. So, you have y times y times y times y, x times, which would be equal to y to the x. And we can double check by using the chart, which is u to the b power. And since they're the same and use the same formula, they should be equal, and that means they're correct. So, yeah. So let's give an example as to why this is correct. So let's say that we start with Alice, who can go to any of the Y couples, right? So this means that she has Y choices to choose from. So from the product rule that we learned about last time, we multiply that with all the other subparts of the possibilities. So, for example, if Bob now were to go to any of the couples, it doesn't matter which way Abby went, or whatever, Alice went. So it doesn't matter. He can go to the original couple, or any of the other couples that they have offered, because there's no restriction as to how many kids one couple can have. So, bam, you have Y couples to choose from times Y, X times X for each kid. So that way, when you multiply them all together, then you get Y to the X power. So yeah, you got it. So let me just explain this one more time in case you don't understand. So based off of the product rule, which states that you multiply all the subparts of the probabilities together to get the number of possibilities that you can get, or you multiply the possibilities, the subparts of the possibilities together to get the total number of possibilities. So by multiplying y by itself x times, you get all the different combinations of, or all the number of possibilities that there are for these kids to get assigned to these parents or couples. So yeah, congrats, you did it. I'm sorry, that was like a really bad explanation, but hopefully you understand it. Yeah, so if not, then no worries. A lot of this has to do with like combinations and permutations, like I said, which we haven't really gone over yet. Hopefully in another video, but we'll see about that. For now, just maybe pause the video and maybe process a little bit, or like pause and like go back. I don't know, whatever suits you. I will also soon be posting like practice problems at the very end, so you can always practice now if you want, or it all depends on you. So yeah, that's it for number 1. Yeah, cool. So now that we've hopefully maybe mastered number 1 type problems, let's move on to a number 2 example. So this particular question, oh yeah, you did it. Okay, so this particular question asks, what if each of the y parents can only take at most 1 kid? So because we know that each couple can have at most 1 kid, we know that it is an injective question. Injective just means that you can only have 1 output, or 1 input per parent. So this means that there has to be more couples than kids, or else there would be 1 parent. And by the pigeonhole principle, that has more than 1 kid just because there are too many kids. And because this is an extension of the previous problem, you know that both variables are distinguishable. And with this example, we once again assign the kids to couples. Because the dogs are because the kids, are distinguishable. So like Abby going before Bob would be different than Bob going before Bobby. The order doesn't matter, and this is a clue that we need some sort of permutation. So here's my work. Let me show you. So although the first kid, like in the question above, has y parents to choose from, the next kid cannot pick the parent that the previous kid picked. So it has 1 less parent to choose from. The third cannot pick the previous 2 parents, etc. So the x kid cannot pick either of the first b minus 1 new parents. So it has y minus, in parentheses, x minus 1 choices. So the total number of injective functions from kids to parents is y times y minus 1 times all the way to y minus, in parentheses, x minus 1, which is equal to below. So yeah, just as the chart predicted, that answer would equal to the permutation of p, and in parentheses, u and b, the permutation of ub. So yeah, like I said, I know I didn't go over like permutations that well before, so if you have any questions or you want me to post another video, then feel free, comment, or just let me know, and I will try my best to give you an answer in a timely manner. So yeah, just a disclaimer though, for these type of problems, that's what the I is for, by the way. This will only happen if u is greater or equal to b. Just because, like I said, or else it doesn't make sense that there are more kids than parents, because we need all the kids to be adopted. So yeah, anyways, good job guys. We did it. Like I said, it's okay if you didn't understand everything, but just give it time to process. If you want, you can skip to the extra problems at the end, but I promise that you guys are doing great. So now we can move on to the last type of problem for the day. So, here's the problem. What if the parents refused to go home until they had at least 1 child? Or, I don't know, I wrote it, yeah, basically like that. In this problem, we have a surjective instead of an injective problem. Despite how suspicious they may seem in real life, we will try to ignore the weirdness of the question for a bit to complete the problem. So surjective just means that every couple has to have at least 1 kid. So in order for every couple to end up with some amounts of kids, we have to guarantee at least 1 kid to each couple without overcounting. So this means that there have to be enough kids to go around, and that the number of kids have to be greater or equal to the number of parents. So this one's a little tricky just because it's hard to guarantee that each owner gets at least 1 dog without I'm getting my analogies mixed up. This one's a little tricky just because it's hard to guarantee that each owner... Oh, sorry, no, I missed it. Okay, anyways, I didn't mean to show you that. But yeah, this means that there has to be enough kids to go around, and the number of kids has to be greater or equal to the number of parents. So that way, each one is guaranteed 1. This is also by pigeonhole principle. So, yeah. This question's a little tricky just because it's hard to guarantee that each couple gets at least 1 kid without overcounting. So instead of counting each individual scenario, which would be impossible depending on the problem, we will use the number of surjective functions when the owners are actually indistinguishable and multiply that by the number of ways to order the owners again. So that way it makes the indistinguishable distinguishable. So later on in case 9, you should definitely check it out. It'll be in a new video soon. We will see that there are S stands for sterling, by the way. Oh, I didn't write it. Okay. So, let me, S, B, U. So the S here just means sterling. So this is a completely different concept, so I'm not going to go over it in this video, or else it'll be too long and too complicated and too much information at the moment. So, yeah. So, there would be SBU, ways to map the number of distinguishable kids to indistinguishable parents. Then, since our function is surjective, every owner has at least one dog, so we multiply with the factorial of U. To make the parents with kids distinguishable, as they should be, we multiply, yes. So, yeah. So, we will see that there are sterling number of BU ways to surjectively map the number of distinguishable kids to indistinguishable parents, S signifying the use of sterling numbers, as I mentioned before. Then, since our function is surjective, every owner has at least one dog, so we multiply by U factorial to make the parents with kids distinguishable as they should be. Sorry, there we go. So there are X factorial times sterling number of XY surjective functions from X distinguishable kids to Y distinguishable parents. I know this wasn't the best explanation, but just because sterling numbers, like I said, is a whole different concept, I decided not to go over it in this video. Writing the answer in the form I just gave you should be fine, though. So, if not, you'll for sure get, like, mostly partial credit. So, I would say not to worry about it too much, but definitely comment below if you want a video to cover it. But yeah, good job, guys. I'll end before the practice questions with the motivational pun of the day. Whoa, that's not it. Whoa, I don't know why I'm... Technological difficulties. Cool. It says, you can do it, you've got this, and it's encouragement, get it? Haha. Okay, cool. So I'll give you 5 seconds to soak in the motivation from this picture, and then we'll move on to the practice problem. Okay, cool. Now I'm going to have the questions appear, and like I said, you guys are super amazing.